Hello students! In this video we're going to discuss electron configuration. Electron configuration describes how the electrons are arranged in orbitals of the atom. And specifically we do ground state electron configuration in this course. So in ground state electron configuration we arrange the electrons in orbitals that give the atom the lowest energy possible. Now there are rules we have to abide by when we're doing electron configuration. One of the first rules or principles is called the Aufbau principle, which represents the build, also known as the build-up principle. And essentially what this principle says is that we fill electrons in the lowest energy orbitals before we start filling in the higher energy orbitals. So orbitals filled in order of 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 4d, etc. So we have to fill the electrons in that order. So we start from the lowest energy level and we work our way up to the highs. The other principle that we touched on in the previous video is called the Pauli exclusion principle, which just simply says that no two electrons occupying the same atomic orbital can have the same four quantum numbers. So if you have two electrons occupying the same atomic orbital, then their spins must be paired. So remember I drew this guy here. We'll do a orbital box. So if I have two electrons, let's say this is an s atomic orbital. If I have two electrons occupying this atomic orbital, one spins up and the other spins down. That is what is meant by spin paired. I cannot have two electrons occupying the same atomic orbital in which both have the same four quantum numbers. So, for instance, I can't have a situation like this. All right. Now, these two electrons have the same principal quantum number and have the same angular momentum quantum number L and have the same m sub L or magnetic quantum number, but their spin quantum number is different. One is plus 1/2 and the other is negative 1/2. And so whenever we put two electrons in an atomic orbital, they have to be spin paired. That minimizes electrostatic repulsive forces, which lowers the energy for the particular atom. All right, the second rule is called Hund's rule. So Hund's rule says that in a degenerate orbital, and what degenerate means is that the orbital, the orbitals are in the same energy level. Okay, for instance, a p atomic orbital. All right, it has a p of x, a p of y, a p of z. So maybe we could say 2p x, 2p y, 2p z. And so what that means is that these p atomic orbitals are degenerate because they're in the same energy level. All right. At any rate, Hund's rule says that in a degenerate orbital, for example, a p atomic orbital, electrons are first singly filled with the same spin before they are double filled in the same orbital. So we first singly fill the electrons. So let's say if I had this. Let's say if I had 4 electrons, I had to fill in the p atomic orbital. So the first 3 would occupy singly each p atomic orbital, and then I would go back and double fill with the opposite spin. I wouldn't want to do this. This would be a violation of Hund's rule. If I took 2 electrons, put them here, and then took 2 electrons and say put them in the, so I got 2 electrons in a p of x, and then I got 2 electrons in a p of y, and then P of Z is empty. This would be a violation of Hund's rule. I must first singly fill the electrons before I start double filling. So, like so. And then notice that when I singly fill, all the electrons have the same spin. Once I start double filling, the second electron will have an opposite spin of the first electron. Okay, so that's Hund's rule. All right, so let's talk about doing electron configuration for the periodic table. So this is your periodic table. It's laid out quite well to do electron configuration. First thing I would like for you to do when you're using the periodic table to do electron configuration is bring helium over here. So I'll just write a box here and put a helium, and I'll put the atomic number above. Alright, so that's helium. Alright, so I'll scratch this one out here because we're not going to need it. Now, let me do some house cleaning here. I'm going to erase this. Alright, I was just showing you how to bring that over there. Okay. Alright, so the first two columns are what we call groups. That's going to be your s atomic orbital. Alright. The rows, or what we call periods, correspond to the energy level. So this is N right here. So this first row is energy level 1, second row is energy level 2, third row is energy level 3, fourth row is energy level 4, fifth row is energy level 5, sixth row is energy level 7, and seventh row is energy level 6, and seventh row is energy level 7. Okay, so the first two columns is the s atomic orbital, will represent the s atomic orbital, and you come over here, the first 6 columns over here will represent the p atomic orbital. Remember, s holds a maximum of 2 electrons. Okay, so that makes sense. P holds a maximum of 6 electrons. Check it out. 1, 2, 3, 4, 5, and 6. And then we have D right here. D is going to come right here. And remember, in D we hold a maximum of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. And then down here we have our F atomic orbital, which holds a maximum of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons. Okay? So, now with the F block, it's going to sandwich in between right here. Alright? And likewise, this one will sandwich right here. So this is 4F, and this is 5F right here. Okay? So it's going to be D1, and then the F block squeezes in between D1 and D2. So if this would be, this is 4S. D is always 1 less than S. So this is 4S 3D. This is 5S 4D. And this is 6S 5D. Okay. And then this is 7S 6D. So it will be D1. So 5D1, and then F4 sandwiches in between 5D1 and 5D2. Alright, and F5 sandwiches in between 6D1 and 6D2. All right. Okay, so now that we know where our atomic orbitals are in the periodic table, now we can start to do electron configuration. All right, so let's start with the easy one. We'll do helium first. So if I said do the electron configuration for helium, well, helium is in the first energy level and it's in the s atomic orbital, so I'll write 1s and just count the number of electrons it has. 1, 2. All right, so I'll write a superscript of 2, so it's 1s2. This is the electron configuration for helium. Okay. So this corresponds to the energy level. This, of course, is your atomic orbital, and this is the number, the superscript is the number of electrons that are in that particular atomic orbital. All right. So let's do the electron configuration for, let's make it oxygen here. All right. So we're going to use the build-up principle here. So what we're going to do is in oxygen, neutral oxygen has 8 protons, so that means it's going to have 8 electrons. So we got to account for 8 electrons here. So we're going to use the build-up principle where we start at the lowest energy level, which is 1. So we'll go through energy level 1, and then we'll get to the second energy level, okay, and we'll go through the S, so it'll be 2S, and then we'll get to 2P, all right, and so 2P, that's going to be 2P1, 2P2, 2P3, 2P4, all right. So we go 1S2, we had to go through 1S, so that's 1S2. We had to go through 2S, so that is 2S2, and then we get to 2P. So we count, now that we're in 2P, we go 1, 2, 3, 4, so that's 2P4. Okay, so this is the electron configuration for oxygen. We said that oxygen has an atomic number of 8, and so that it's neutral, so that means that it's going to have 8 electrons, 8 protons. So we add up these superscripts and we'll get 8 electrons. So 2 plus 2 is 4, plus 4 is 8. So this is the electron configuration for oxygen. Now I can write this another way. I could do what this is called the condensed ground state electron configuration, and I'll just abbreviate here, config. Okay. All right, so we can do something called expanded ground state electron configuration. Check this out. So this will be 1s2, 2s2, and remember the p atomic orbital has a p of x, p of y, and a p of z. Okay, so now this is where Pauli exclusion principle, no, Hans rule is going to come into play. I'm going to write a 2 right here, a 1 right here, and a 1 right here. So let's use an orbital diagram box to kind of show what's going on here and how Hans rule comes into play here. So this is my 1s2. So I got 2 electrons in the 1s2. In the 2s2, I have 2 electrons. And this will be 2px, this will be 2py, and this will be 2pz. Alright? So remember, Hans rule says we first singly fill the atomic orbitals. So that's what I'm doing here. And now I'm gonna go back and double fill with opposite spin, of course. So this will be 2px2, 2py1, 2pz1. All right, and we call this expanded ground state, ground state electron configuration. Expanded ground state electron configuration. Okay. There is another way for us to represent this, and we can use something called noble gas notation. So we look at the noble gas that comes before the element in which we're doing the electron configuration for. In this case, the noble gas is helium. Your noble gas, this is your noble gas column right here. This column right here represents your noble gas column. These are the most stable elements on the periodic table. All right, and so the noble gas that comes before oxygen is helium. So we'll write helium in brackets. And then we write everything else, right? So that'll be 2s2, 2p4, all right? So helium has an electron configuration, recall, of 1s2, all right? So that takes care of that. And then we just write the rest. These are what we call valence electrons. Valence electrons. Valence electrons are the outermost electrons, and those are going to be the electrons that participate in chemical bonding. Okay, the core electrons are all the electrons that are closest to the nucleus. So those, if you do the noble gas notation, the noble gas is going, the noble gas that's in brackets, that's going to be your, essentially your, whatever the electron configuration is for the noble gas, that's going to be your core electrons. Okay, so this is called noble gas notation. All right, noble gas notation. Okay, so with some practice, you'll get this. So let's look at another one. All right. So again, bring your helium over here. So helium is over here. Let's do the electron configuration for magnesium. All right. So this is S. This is the S block. This is the P block. This is the B block, and of course this is your F block. All right. So we're going to do the electron configuration for magnesium. So magnesium has an atomic number of 12. It's neutral, so that means it has 12 protons and 12 electrons. So we got to account for 12 electrons for magnesium. So of course we start at the lowest energy level. This is 1s, 2s, 3s. Magnesium is in the third energy level, so we have to go from the first energy level to the third energy level. So in the first energy level, we have 1s atomic orbital. So we're going to fill all the electrons in that atomic orbital. So that's 1s2. In the second energy level, we have 2s as well as 2p. We start with 2s. So we'll go through the 2s atomic orbital. So we'll fill all the electrons in the 2s. So that's 2s2. And then we'll go to the 2p, and we'll go all the way through the 2p. So that'll be 2p6. All right. So we fill all the electrons in the 2p. So that's 2p6. And then we get to the third energy level. Magnesium is in the third energy level. It's in the s atomic orbital, or the s block, and it is 1, 2. Okay, so what that means is that that's 3s2. So the electron configuration for magnesium is 1s2, 2s2, 2p6, 3s2. Now, how would I write the noble gas notation for this? Well, let's look at the noble gas that precedes magnesium. Again, this column is the noble gas column. Okay. And the noble gas that precedes magnesium, of course, is neon. Well, check this out. This is the electron configuration for neon. 1s2, 2s2, 2p6. So we'll write neon right here in brackets, and then we'll write 3s2. So if you were to be asked, okay, well, how many valence electrons does magnesium have? You would say 2 valence electrons. Two. I should have said, yeah, I should have said two valence electrons. Okay. And these electrons here are the core electrons. These electrons are closest to the nucleus. Notice the core electrons are completely filled. The atomic orbitals for the core electrons are completely filled out. You completely fill out the energy level for the core electrons. Okay? All right. So, let's look at doing the electron configuration for chlorine. All right. So chlorine, it's 17. It has atomic number of 17, so that means it's going to have 17 protons, and it being neutral, it's going to have 17 electrons. All right. So we're going to start at the lowest energy level, which is 1. So we'll say 1s, and we're going to go through that, 1s2. And then the second energy level here, we're going to go through 2s2. So we'll account for both electrons in that atomic orbital. And then we're going to go through the 2p atomic orbital. So that's going to be 2p6. Remember, p holds a maximum of 6 electrons. 1, 2, 3, 4, 5, 6. And then we're going to go through the 3s, and that's going to account for all the electrons in that atomic orbital, so 3s2. And then we get to 3p here. So this will be 3p1, 3p2, 3p3, 3p4, 3p5. So this is 3p5. So kind of 1, 2, 3, 4, 5, 3p5. So that is our electron configuration for chlorine. All right. Now we could do the noble gas notation here, chlorine, and then write the noble gas that comes before chlorine is neon, so we'll write that in brackets. So that'll account for all of the electron configuration here. And then we simply write 3s2, 3p5. So chlorine has 7 valence electrons. It is the valence electrons that are involved in chemical bonding, and so these will represent the core electrons. These electrons are closest to the nucleus. All right. All right. Well, what happens if I have magnesium 2+? What would be the electron configuration for magnesium 2+ ion, cation? All right. Well, when we lose electrons from the highest energy level. And so having a +2 charge means I've lost electrons. Remember, in cations, you lose electrons. The magnitude of the charge will tell you how many electrons you lost. So if we were to do the electron configuration for magnesium cation, it would just be 1s2, 2s2, 2p6. All right, what about chlorine gaining an electron to become chloride? What would be the electron configuration for chloride? Well, this is an anion. Okay, so in anions, your atom gains electrons, and based on the magnitude of that negative charge, it tells you how many electrons it gained. It turns out that this chlorine gained 1 electron to become chloride. And so the electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6. All right. So let's do a couple of more. Let's tell you what. Let's do iron here. Let's do iron. All right. So iron is going to be 1s2, 2s2. So we're going to go through the 1s, the 2s, 2p. We're going to go through 2p, so that's 2p6. And then we're going to go through 3s, so that's 3s2. And then we're going to go through 3p, all right? So that's going to be 3p6. And then we get to 4. So we go through 4s. So that's going to be 4s2. D is always 1 less than s. So if this is 4s, then this is 3d. All right, so we go 3d, and then we count 1, 2, 3, 4, 5, 6. So that's going to be 3d6. All right, so what if we had iron can lose 2 electrons, or it can lose 3 electrons? So you can have this, you could have an iron +3, or you could have an iron +2, or you could have an iron +3. So what would be the electron configuration for iron +2? Well, remember I said when you lose electrons, you lose from the highest energy level, right? What's the highest energy level here? Well, 4 is higher than 3, so I'm going to lose electrons from the 4s2 orbital first. So that's going to give me 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. All right, I lose both electrons from the 4s2 because 4 is higher in energy than 3. All right, so having that in mind, what about iron 3? Well, that's going to be 1s2, 2s2, 2p6, 3s2, 3p6. I'm just going to lose an additional electron from the D, so that gives me 3d5. All right. Of course, I could have done this using noble gas notation, right? So 1s2, 2s2, 2p6, 3s2, 3p6. That's the electron configuration for argon, so I put that in parentheses and then just simply write 3d5 here. And again here, this would be argon in brackets, and then write 3d6 here. Of course, this would be argon in brackets, and then I write 3d6 4s2. 2. The reason why I flipped it is because 4 is higher in energy than 3. You're going to lose here first, and then you'll start losing from the 3D. So I hope this video was helpful. I will do some more electron configuration with you guys. I'll post some more examples so that you get a feel for this. All right. So until the next video, as always, happy studies.